Welcome back, calculus students, to what should be the fifth and final installment in the video series for limits at infinity and sketching the graph of a function. We have another rational function, very similar to the last one, except you can see the degree in the numerator is higher than the degree in the denominator. So this triggers the fact that there will be a slanted asymptote for this problem. Step one is to check your domain, which should be all real numbers, where x is not equal to positive 1, since positive 1 is going to give us a divide by 0 error from our denominator. We also know that x equals 1 is going to be the location of the vertical asymptote because of this. Step 2 is to find the x and y intercepts. So if you plug in 0 to this function, you're going to get 0. And that actually represents the x and y intercept both, because there are no other values of x that will make this numerator equal to 0. Step 3, vertical asymptotes, is done, and we're ready for step 4, which is to take the derivative of the function. We haven't done the limits. Hang on. Let's take the limits of this function. I've already lost my order for my steps, but I know that this is in there. What is the limit as x approaches infinity? And I'm going to factor out an x, not an x squared, from each term. So that's going to give me x over 1 over x, nope, taking out an x, that's going to give me x over 1 minus 1 over x. My denominator as x approaches infinity is going to approach 1, and my numerator as x approaches infinity is going to approach infinity. So I know that the limit as x approaches infinity is infinity. And I can also tell from the scratch work that the limit as x approaches negative infinity of f of x is just going to be negative infinity. Next, I'd like to take the first derivative of the function using the quotient rule and locate any critical values. So we've got the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Automatically, 1 is a critical value because it's an asymptote. And then we need to solve the numerator in order to figure out any other critical values. So it looks like the numerator is 2x squared minus 2x minus x squared. Which gives us x squared minus 2x. That expression is factorable. We're going to get x minus 2. And so we have two additional critical values, one at x equals 0 and one at x equals 2. I am going to erase my scratch work from the previous problem just to give myself a little more space to sketch this graph. Because this took up a ton of space up here. Okay, got some room to start my graph and do my sign chart and all that good stuff. So sign chart, I'm just going to do it down here so it's near my work. I've got 0, positive 1, and positive 2 as critical values. And so I'm going to choose negative 1, 0.5, 1.5, and 3 for test points, and I'm going to plug each of these values into my first derivative over here in its factored form. If I plug in negative 1, I am going to get a negative, negative, and the denominator is always positive. So two negatives make a positive. If I plug in 0.5, I'm going to get a positive, a negative, and always positive. If I plug in 1.5, I'm actually going to get that same result. And so you can see that 1 is not a local extrema, which we already knew. We knew it was an asymptote, but this confirms it because the derivative does not change signs. Finally, plugging in 3, I get a positive. So now I know x equals 0 has to be a maximum, and x equals 2 has to be a minimum. Let's start putting these pieces on the graph. I've got asymptote at 1. I've got 0, 0. I've got a maximum at 0, 0 Oh, that's interesting. So I know that it has to be decreasing this way. And I also know it's actually got to decrease that way too. And then 2 comma, I don't know, we need to plug it into the original function way back at the beginning. So I'm going to switch colors to blue, and I'm going to plug in 2 to find my minimum. And that's going to be 2 squared over 2 minus 1, which means 4 is the minimum, 2 comma 4. 1, 2, I'm going to cheat, go 1, 2, 3, really crowded. So 2 comma 4 is a minimum, which means that the function is decreasing leading up to this point and increasing afterwards towards infinity. And so I don't actually know the equation of the asymptote, which is what I would normally do in an algebra class, but this is my calculus approach. So the only other thing we should check is the inflection change. You can see that it's concave down to concave up. My guess is that the inflection point is at 1, but I like to show that second derivative and show that scratch work to confirm. So my f prime x simplified is x squared. Oh, I actually have it simplified, just kidding. The fx, the derivative that I'm going to be focusing on for my second derivative, is this one right here. Okay? So the derivative of the numerator is 2x minus 2. I'm going to have to write a lot smaller if this is going to fit. We've got the numerator unchanged. It's still not going to fit. Times the derivative of the denominator. 2 parentheses on that. All over the denominator squared. Since it was already squared, it's going to be to the 4th. It's hard to tell with my handwriting, but it looks like I can take out an x minus 1 from both terms. Actually, looks like I can take out a 2x minus 1 from both terms. So that's going to leave me with, I'm going to try to highlight this in like, I guess, pink. So I'm taking out this 2. And if you actually look at it, this whole factor right here is a 2x minus 1 factored. So I'm going to take that whole term out, that whole factor, that expression, and then I'm going to be left with, if that's gone, I'm left with x minus 1 squared minus, and then this whole thing is gone. Let's put that in pink. This is also 2x minus 1. So minus x squared minus 2x. I would pause the video here and go ahead and distribute out this x minus 1 squared and combine like terms, and then unpause the video and compare your results with mine, because I'm going to be skipping a lot of that scratch work. So that gives me 2x minus 1. Ooh, those can cancel. We'll get there. I'm getting distracted. And then over here, I've got x squared minus 2x plus 1. Minus another x squared plus a 2x. And so the x squareds are going to cancel. The 2x's are going to cancel. And I'm just going to be left with 1. Oh, that's so lovely. That whole expression is just 1. Okay. From here, these cancel, and I'm left with 2 over x minus 1 cubed. Thankfully, it's cubed because a cubic can actually change signs. If this was squared or to the 4th, it wouldn't change from being positive to negative, and then we would have no inflection point, which completely goes against what our graph is showing us. So x equals 1 is our inflection point. That makes the denominator equal to 0, which means that the second derivative is undefined. And if you plug in a value less than 1, such as 0, you're going to get a negative, which is why we're concave down. And if you plug in a value greater than 1, like 2, you're going to get a positive, which is why we're concave up. So 9.5 minutes to do one problem. Let's do another one. We have x minus 1 to the 2/3, which is a radical function, and we're going to repeat the process. Because this is a cube root, remember your rules here. It actually has an infinite domain. We can't plug in anything here that's going to cause an error. Cube roots accept both positive and negative values. So my domain is all real numbers. My x-intercepts and y-intercepts. So if I plug in 0 to this function, I get the cube root of -1 squared, which is the cube root of 1, which is just 1. And then if I set this to equal to 0, I'm basically setting the interior equal to 0. So when does x minus 1 squared equal 0? It's when x minus 1 equals 0, which means it's when x equals 1. So my x-intercept is at 1, 0. Next step is to evaluate the limits as x approaches infinity of this function. So we've got our limit as x approaches positive infinity, and I am going to rewrite this as the cube root of x minus 1 quantity squared, and I'm going to rewrite it one more time. The limit as x approaches infinity of the cube root of x squared minus x 2x plus 1. And this leaves us with a really interesting function because it's not rational, right? So it doesn't really have any of the rules we're looking for. If you imagine as x approaches infinity, so put something, why can't I add notes? Infinitely large here. You're going to square it infinitely large, and you're going to cube root it infinitely large. So the limit as x approaches positive infinity is just infinity. Now imagine that this was negative infinity instead. If you plug in a negative value here, you're going to subtract 1, which is just negative infinity. Taking negative infinity minus 1 is just still negative. But then you square it, and it ends up being positive. So it turns out the limit as x approaches both positive and negative infinity is infinite. This function doesn't have any vertical asymptotes because it doesn't have a denominator. So we're ready to take a derivative and take a look at the extrema. So let's do f prime of x, and we're going to bring that 2/3 forward, turning it into a fraction, because when you do minus 1 in this numerator, you're going to get a negative 1/3, and I'm going to go ahead and toss that in the bottom as a cube root, x minus 1, and I want to set this equal to 0, but if the numerator is just 2, this function is never equal to 0. So it doesn't have any critical values that make it 0. It only has a critical value that makes the denominator equal to 0. And that critical value is x equals 1. So we're going to be evaluating how the first derivative behaves at values less than 1, such as 0, and values greater than 1, such as 2. If you plug 0 into this first derivative, you're going to get the cube root of -1, which is -1, and so you have a negative. And if you plug in 2, you're going to get the cube root of +1, which is positive, so we have positive. And so it turns out that 1 is a critical value. So 1 is a critical value where the derivative is undefined. Well, let's take that 1 and let's plug it back into the original function. F of 1 is equal to 1 minus 1 to the 2/3, and so it's equal to 0. Since it goes from negative to positive, we can say that we have a minimum of 1, 0. Now this is strange because we know that the derivative is undefined, so we must be looking at an asymptote, which we're not, we've already ruled that out, a corner, think of like an absolute value function, or a cusp. So when we go to sketch the graph, because we are looking at a cube, that's a curve and not linear like an absolute value would be, we are going to attempt to sketch a cusp at 1, 0. We also know that's the x-intercept, and that there's a y-intercept at 0, 1, and that the function is decreasing before this and increasing after. Let's go ahead and find the second derivative real fast. I'm going to take my first derivative back to its negative exponent form, which is 2/3 x minus 1 to the -1/3. And I'm going to derive that again. I'd like to get the inflection points drawn on the graph, just to help my shape. So if I multiply these, I'm going to get -2/9. And then I'm going to drop this back down to the denominator. If you minus 1, it becomes x minus 1 to the 4/3. And again, that numerator can't ever be 0, but it can be undefined because of the denominator at x equals 1. So the inflection point where it changes concavity is also 1. If I plug in a number less than 1, like 0, I'm going to get an overall negative result because of this negative up front. So 0 minus 1 to the 4th power is positive, times a -2/9 is negative. So I know that my function is concave down, crosses through 0, 1, and forms a cusp at 1, 0. And then if I plug in +2, again, this will turn positive, but the overall result is negative, so I need to remain concave down for the other side. An infinite domain means arrows on both ends. This concludes the 5th and final portion of the video notes for the lesson on limits at infinity and sketching graphs. Thank you for watching.